So, hello everyone. Yesterday we had done some we had completed KCL and KVL in the discussion, and today we shall carry on discussion on nodal analysis. Okay, so today we'll try and do a few numericals based on nodal analysis, and also some basic questions like which probably will just give you an insight on how to approach a given question. Okay, I've been repeating this for in every lecture of mine that in network theory, all you need to do is approach any question step by step, utilize all the information that you have given in a question, and it will be a very smooth sail for everyone here. Okay, so for today, let's take this one to be our first question for the day. Okay, what does the question say? The question asks us to determine V1 and V2 and E. See, where is V1? Okay, let's see where is V1. V1, this is the voltage it is asking us. This is the voltage it is asking us to determine, and this is the voltage it is asking us to determine, right? Now, let us see what else is given. Okay, see, we are given with uh, a ground potential here, a 1 volt potential here, similarly 3 volts and 2 volts, and every other point is marked. This is 10 volt positive 10 volt here, right? This is positive 10 volt here. Now tell me, can you find out the absolute potential at point A with respect to ground? With respect to ground, can you find the potential at point A? See, it's very easy. How would you do it? See, this is 0. When you travel, again, when I say when we are traveling in a loop, what do we do? Whenever we are traveling from higher potential to lower potential, how do we signify it? We signify it with a negative magnitude, right? So how would you write VA to be? See, your VA is equal to, this would be 0, right? Positive to negative, we are always losing energy. So what would we write? Minus 1 volt is equals to this potential, right? See, we complete this loop right like this. If we draw an imaginary loop like this, can we find out the potential of point A with respect to ground? It is with respect to ground. I'm just denoting it with a small 0. Okay. So what is the potential at point A with respect to ground? It is minus 1 volt. Is it clear? Similarly, now focus here. This time we need to find out the potential at point B. Again, if this is 10 volts, there must be, this 10 volt would be with respect to some ground, right? This would be with respect to some ground, right? So this is 10 volt higher from ground because it is the potential given provided here. From 10 volts, see, now we are calculating potential at point B with respect to ground. Now tell me, what would it be? Would it be 10 volts, right? We're traveling from, this is 10 volts given, right? Now this time we're traveling from negative to positive. You are supposed to be, doing work. Whenever you're doing work, you write a positive sign for it. So what would it be? Plus 8, right? Right? So what is the potential here? 18 volts, right? Now tell me, what is E? What is E? Can I write E to be VAO minus VBO? Isn't it the potential difference between point A and point B? Would it give me the potential at point E? Right? Rather this potential difference, can I get it? So when point A and point B are known. See, this is at higher potential. So we'll subtract potential A from B. What would it be? This would be equal to minus 1 minus 18 volts. That would be equal to minus 19 volts. This is your potential which was asked in the question. This is the step 1 that we've solved, right? Are we clear? Okay. Now, see, in this step, we did reach the potential at point B to be 18 volts, right? The potential of point A to be minus 1 volt. All we need to do is find out the potential V1. Tell me what is V1. Can I write V1? See, assume this to be a loop. This. I am taking point B and then returning from here itself. We are drawing an imaginary loop. Let me change the ink color so that you can understand better. See, if I make a imaginary loop and see I'm just taking point B and nothing else. Okay. So this V1 would be with respect to some ground. So there must be some V1, right? Negative to positive, there is potential V1 that is applied. Okay. Now you're traveling from, tell me, you're traveling from negative to positive. Whenever this, whenever we're traveling from negative to positive, whenever you're traveling from negative to positive, what do we write? Plus 2 volt, right? Right? And this time it is at a higher potential and we are going towards ground. We are going towards ground. This V1 would be with respect to some ground. So this should be minus 18 is equals to 0. Or can I write, tell me, can I write V1 is equals to 16 volts? It's a very simple way to approach questions. See, this has got nothing to do with nodal analysis, right? This has got nothing to do with nodal analysis. All I need you to focus in this question is to understand how to approach such questions and also understand how to approach questions based on network theory in general. In network theory, there's nothing difficult about the questions. All you need to understand is you need to exploit whatever has been given in the question, and then you can very easily solve such questions. Here you will, if you see the question at once, you will find that you may probably believe that there's nothing given. How can you find V1 and V2? But now when you look closely, you're given the potential at point A, you're given the potential at point B. Would it be difficult to find E? Which is, what is it? It is just the difference between potential A and potential B, right? Right? So now that we know, we have calculated V1 to be this. Now using the similar approach, again we'll be traveling in this loop. See, this is the loop we'll be traveling in. Okay. Now tell me, how would you calculate V2? See, this time V2 would be V2. Again, we're traveling from positive to negative. Whenever the traveling is from positive to negative, we denote it with a negative sign. So this would be minus 3 volt, right? Now the potential at point A would be what? It is minus again, and what it is denoted as minus 1. The potential at point A is with respect to ground. With respect to ground, it is given to be what? Forget about the magnitude. It is given with respect to ground. So whatever is the magnitude, we'll write VA minus ground. Now, it is again, for once we'll take it as negative and then we'll replace the value as it is, right? So what would we get? V2 to be 2 volts. This is how would you would approach questions based on, this has got, again, I'm repeating, this has got nothing to do with nodal analysis. It is just a basic implementation of KCL and KVL you've learned so far. Rather, in this case, it is simply KVL. It is not even KCL, it is just KVL. All you need to understand is how to find out absolute potentials, and find out what is given in the question, right? Chalo, let's move on to the next question, and this is where you will learn what is, you'll begin to understand why nodal analysis is easier, and probably you can use it as a approach to solve your questions. See, what did I tell you in when we were studying nodal analysis in the last lecture? What did I tell you? First thing is to to identify nodes. Changing the pen color here. Now, tell me, I'm traveling from this point to every point in this network. Tell me, what would this be a node? See, whenever you encounter any element which is supposed to change the potential of the, you know, of this point. See, this was a conducting pair, and now you encounter a 8 ohm resistor. So there will be a change in potential. So yes, this is a node, right? But tell me, have I not defined this node as of now? See, this is already defined. How is it defined? Because this is at potential P. This is node VP. We have already given it a name, haven't we? Why? Because this is at the same potential. It is short circuited here. So this is VP. So I can also write this to be VP, right? So, right, this is the same point. Okay. Now, if I travel from this point to this point, this is a current source. Again, there will be a change in potential. Yes, you encounter any element and you see, yes, there will be a change, and so you will find a node here, which is again already defined for you in this question, right? So you don't need to mark it again, right? If you travel from this to this, yes, it is a node. There is no doubt it is a node, because you encounter some element. Whenever there is an element, there is a change in potential. There is supposed to be a change in potential, and hence this would become a node. But have we not defined it? We did define it. What is it? It is VQ, because it is short circuited. It is at the same potential. So if I write VQ here and if I write VQ here, it is the same thing. It won't change. Now, tell me, when I travel from this to this, yes, this is a node, and it is not defined so far, right? It is not given to you in this question. Tell me, what is this node? Let me name it, say, PQ. Let's say it R. Can I, using this question, define what is VR? See, this is a potential, this is a node, this is a node. Now tell me, can I define VR from this point? See, it's very easy, because we are traveling from the ground to this point, and there's a 100-volt voltage clearly given in the question. VR would be equal to 100 volts. Okay. Again, in network theory, in questions relating to basic KCL and KVL and probably nodal analysis, all you need to do is focus on whatever is given in the question itself, and you will be good to go. There is nothing difficult about such questions, right? So now that you are given VR, now tell me, we have this node, we have this node, and we have this node. Now let us apply KCL on the node P. So what does KCL say? KCL say, at any point of time, the sum of currents at any node, at any point of time is equal to 0, assuming all currents to be outgoing. Assuming all currents to be outgoing, tell me, how are we going to write this? So tell me, what is the current in the 8 ohm resistor branch? What it would be? Now we are assuming an outgoing current. How would we write? Vp because we are assuming outgoing current, so P will be at a higher potential minus, what is the potential here? It is 0, Vp minus 0 upon 8, right? Plus, tell me, Vp minus Vr. Now what is Vr? Vr is 100 volts. So can I directly replace it as Vp minus 100 upon 2? See, this would signify what? The current in 2 ohm branch, right? Then tell me, this is outgoing current. It is already defined to be 2 amperes and it is in the same direction as our convention, the outgoing current. So what would we write? Plus 2 ohm, 2 amperes, sorry, is equal to 0. Am I making sense? Right? Now, solving this, for solving this question, for solving this equation, what would we do? Just solving this equation, multiply the entire equation by 8, right? What would it become? Tell me. When I multiply the entire equation by 8, what would it become? Vp, again minus 0 is 0. So, if I multiply it by 8, the 2 cancel out, plus if I multiply it by 8, what would it become? 4 times Vp minus 100 plus 8 times into 2. I multiplied the entire equation by 2. See, I have multiplied this entire equation by 8, right? So this would become Vp. This would become 4 times Vp minus 100 plus 8 times 2 equals to 0, right? Or can I write 5 times Vp, 5 times Vp is equals to 400 is equals to 400 minus what? 16, right? 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 Can I write this to be 384 divided by 5? This is what is Vp for you, right? Are we clear? Now similarly at node Q, tell me at node Q. Assuming again all currents to be what? Outgoing. Assuming all currents to be outgoing. Now assuming all currents to be outgoing, we are simply applying KCL here. Now tell me what would be the current for 6 ohm resistor? Can I write it to be VQ minus 0 divided by 6? That would be the current for, that would be the current for 6 ohm resistor, right? Plus VQ minus VR is again given to be 100 volts divided by what? 4, right? Right? And this time remember, what are we what are we getting? We are getting an incoming current. But what do we take as in our, what is our convention? It is an outgoing current that we have taken. So can I write this to be minus 2 amperes because it is against our convention, right? what is our convention? All out, the sum of all outgoing currents to be zero, but this time the current is incoming. So how would I represent it? I would represent it that a minus 2 current is actually leaving this point. If I say 2 ampere current is entering the circuit, can I, in the same line say, can I say a minus 2 ampere current is leaving the circuit, is leaving this node at Q? So that is what we have represented here mathematically, right? Now solving this equation in this, at this point, what would we do? Let us multiply the entire equation by 12. That is what we do. We have multiplied by LCM. So can I do it as 2? Can I write it as 12 times VQ, again minus 0 is 0, plus 12 times VQ minus 100 upon 4 minus 12 into 2 is equals to 0, right? This would become 2VQ, right? Plus 3VQ minus 300 minus what? 24 is equals to 0. Can I write 5 times VQ is equal to what? It is equal to 324, or VQ is equals to 324 divided by what? 5. This is what we have achieved so far. Now tell me, what was the question that you were asked? You were asked to find out the potential difference Vp and Vq. Now we have already achieved the potential at Vp and the potential at Vq. Now we are supposed to answer what is Vp minus Vq. Vp minus Vq is equals to 384 upon 5 minus 324 upon 5. This would give me what? 60 by 5. Your answer would be 12 volts. Okay? Right? So, this is how you basically approach any question based on nodal analysis. Any question based on nodal analysis, all you need to do is find out, step number 1, identify each node. Step number 2, mark the potential at each node. See, we had already defined, we were already provided with nodes Vp and Vq in the question itself, so we did not need to mark it, but we were not given the node Vr. So we marked a node PR. This is where we have completed our step number 1. Now mark every potential that is given in the question. So we cannot determine what is Vp, we cannot determine what is Vq, but we can still determine what is Vr, right? So mark every potential that is given. Now at any node, beginning with any node, you know, you know, for each we usually choose the principal node, because from there on we'll get a lot of equations right there. So if we get Vp, then we are calculating, assuming all currents to be outgoing, and by the principle of KCL we have the sum of all outgoing currents at any node would be equal to 0. Using such, using such principle we can calculate this question. Okay, this was a simple application of what? Nodal analysis. This is the first time that we have done nodal analysis so far. We did a similar question yesterday on nodal analysis. Today is the second question that we did. This is how you need to approach such questions. Okay. So the next question would be the last question for the day, and this is where we will understand a very important concept. So be very attentive. See, there is a concept called as supernode. tell me what is the, what is supernode? See, what is supernode? Whenever between two nodes, whenever there are two nodes and you encounter what? A ideal voltage source. What do you encounter? A ideal voltage source. In such a scenario, it gets difficult to solve the question using KCL, right? So, so one option could be solving the question using KVL. But usually in T structured networks, it is advised to use a approach of KCL because it's easier to solve question that way. But but when you're provided with an ideal voltage source between two nodes, in such a condition, to determine the current between in this branch, to determine the current between this branch is difficult. Tell me how can you do it, because there is no resistance. The ideal voltage source, so there will be no resistance, and when there will be no resistance, can there be infinite current here? No, right? Because what? The potential difference V1 minus V2 divided by what is the resistance here? V1 minus V2 is 5 given, but the resistance is 0. This is a ideal voltage source, so what? It is 0. So this is definitely not true. So how are you going to approach such question? Tell me. In such questions where you encounter a ideal voltage source between two nodes, what do we do? First and foremost, the first thing that we can see, and again, very important skill in network theory is write whatever you are given in the network. What is the first thing that you can see and you can identify as it is? See, the first thing that we can see is V1 minus V2, which is given in the question, is equal to what? 5 volts. This marks your first equation, right? For the second equation, what would you do? For second equation, what we do is we write all the sum of all outgoing currents from this point, right? All outgoing currents from this point, and we neglect this branch. Okay, let me do it and then I'll explain you. See, what would this be? What would this be at V1? At node V1, what would you write? Again, at node V1, I'm telling, what would you write? You would write, you would write V1 V1, right? Divided by 1 by 2, because the second point is what? Ground. V1 divided by 1 by 2. We are assuming all currents to be outgoing, but this is an incoming current. So how do I signify an incoming current? I would write minus 9, right? Right? Now tell me, now tell me, what about V2? What about V2? Just leave it right here. Now tell me, what about V2? How would we define V2? Can I write V2 upon 1 by 6 minus 4, right? So, in questions relating to supernode, what do? We combine these two conditions here and make, you know, make one common equation. From this is where you will get your equation number 2. Why is it so? Because ideally there should be, ideally what should be here? 5 volt divided by a zero resistance, that should be a huge amount of current. That cannot be true, right? So can I write whatever is the current here would be the current which is here, because at this point would be the sum of currents here. the current in this branch. I am just talking about node V1. If you focus on node V1, the current in this branch is given, the current in this branch is given. Now, for a time being, forget about this and tell me what would be the current here. Would it not be the current flowing in this and this? That is what we have written here. The sum of currents in this branch and this branch would be the current here. So, in easier terms, what we can say, we combine the two conditions at V1 and V2 using a simple plus sign, and that is how we approach. It is nothing but basic application of KCL at this point. At this point, we will get sum of currents. This to be the sum of currents here, and again this would be flowing here, right? So this is whatever I am explaining right now is you need to understand why exactly are we using, why exactly are we combining the 2 points. This current would be what? The current in this 5 volt resistor would be what? The sum of currents here. That is what KCL says. The entering current would be what? Divided into two branches following it, right? So it is entering here, it is leaving here, and here when we have calculated all leaving currents, it should be what? Sum of the two currents in these two branches, right? Now let us solve this for us. Can I write? Can I write it to be 2V1 Can I write it to be 2V1 minus 9 plus 6V2 minus 4 equals 0, right? Or can I write it to be, I am again rewriting it here, 2V1 plus 6V2 is equal to what? 9 plus 4 is 13 is equal to what? If I send it to the right hand side, it would be plus 3 volt plus 13 volt, right? So, in case we need to solve this question, what would I do? I would multiply this entire equation by what? Plus 6, right? So, it becomes plus V 6V1 minus 6V2 is equal to what? 30 volt. 6 5s are 30. And now we'll write V1 minus, rather plus 6V2. I'm just writing it down from the above equation. There's no rocket science here. Right? If I solve this question for you right here, it would be what? 6 plus 2 is 8 volt, and this becomes 43. So can I get V1 equals to what? 43 by 8, right? Right? Now we need to calculate V2, right? We need to calculate V2. V1 is calculated to be 43 by 8 minus V2 is equal to what? 5, or can I write 43 by 8 minus 5 is equals to V2, right? Or can I again write? Tell me, how do you signify this in our simple combination fractions? Can I write it as 40 plus 3 divided by 8 minus 5 is equals to V2, right? What is 40 divided by 8? Is it 5? Plus 3 by 8 minus 5 is equals to V2. You have your V2 to be 3 by 8 volts. So these are your answers. Okay. So today I want you to see a few more questions on supernode. In case you find any, Ask me any doubt that you have on the WhatsApp group that, yeah, we have. And let's see, I'll bring some more new questions tomorrow on the same topic. We can probably, we are rather not tomorrow, tomorrow is Sunday. So we'll continue our classes from Monday. Let's see if we can start with mesh analysis, or we'll bring a few more new questions on nodal analysis. Try and revise whatever we have done so far. It is a very basic class, so a lot of you must be very acquainted with whatever I am discussing so far. But still, just go through it, because it will help you build a lot of concepts. Okay. Okay. Let's meet on Monday, and that's it for today.